Hi, everyone. Welcome to another FLAN Talk. Today, we're excited to have Kyle Richardson. He's a senior research scientist at AI2 working on the Aristo project. He's recently been giving a lot of thought to formal methods in natural language processing, pointing towards perhaps understanding what models know and how to verify the correctness. And today, he's going to tell us about his work on direct preference alignment and understanding that through logic. So we're very excited to hear from him. And Kyle, take it off.
Good. So thanks everyone for coming, and thanks Lena for initiating this. I think Will as well. Um, as Andy just said, today we're going to talk about some work we've been doing on formal characterizations of preference alignment algorithms for language models. So nothing about formal languages, I'm sorry to say, but I'm hoping that we can maybe find some common ground with some of the techniques that we're using here. And this is joint work with Vivek Srikumar at the University of Utah and Ashish, I think most of you know him, who's my colleague here at AI2. Okay. So I'm going to start by setting the scene and just making a few general remarks. First, starting with the obvious, which is that we now have very powerful general purpose large language models, which includes, of course, ChatGPT. Here, I asked it a query about, so I asked it to tell me about the FLAN gathering and did an okay job at doing that. But of course, we use these models not just for our text understanding problems, but we routinely use them for doing things like writing code. We integrate them within complex systems. We're even starting to use them for tasks like scientific discovery. And just to say it simply, models have far exceeded at least my own expectations. And this is in part due to big advances in the pre-training, scaling, as well as things like RLHF and preference tuning, preference alignment, which is what I'm going to talk about today. Now, how do we get to these general purpose large language models? This is just an illustration and a reminder to set the scene. So typically we use a three-stage process. So nowadays models number in the billions of parameters. We train them during the pre-training stage on trillions of tokens. This is then followed by an instruction tuning phase, and this is the point where we start to tune the models on the kinds of problems that we're ultimately going to use them for, problems like question answering, for example. And then this is often followed by a preference tuning stage where we augment the data not just to have outputs, but ranked outputs based on preferences of some agents. And these two stages are commonly what we call model alignment. So again, we're getting the model to do the things that we want it to do, and in some sense in the manner in which we want it to do those things as well. And then finally, this gets us to a general purpose model, and this roughly approximates the kinds of models that we use. Okay, so I'm assuming everybody is familiar with this. People will also know that there are major problems with this overall picture. So the most successful models and the models that most people are using are, of course, the closed source commercial ones like ChatGPT. We know increasingly little about how they work, how they're trained, what the data sets are. And of course, in general, just given the sheer scale and scope of models and data sets, very hard to really understand what's going on in any granular way. So this is an obvious problem for safety in applications, but it's also a problem for deciding what research to do. So when you look at this picture, most of us don't have the resources to be pre-training models. Some of us don't even have the resources to be tuning models at the end stages as well. So how can we contribute in this space? How can we do meaningful research that's impactful, but also that's technically interesting as well? And one of the ideas I want to pitch today is using formal analysis to try to study the semantics of the underlying algorithms that drive these large language models. And we're going to focus, as I said at the beginning, on this last problem of preference tuning here. And in a way, I'm going to try to advocate for a sort of armchair style of NLP. I'm actually not going to talk too much about experiments. And with regard to preference tuning, the questions we want to answer are things like, what do we do when we tune models to preferences? Do these algorithms have an inherent semantics that we can discern? What are the underlying principles that are involved, and can we in some way leverage those principles to help us discover better algorithms? so that's the big picture. And now I'll say a little bit about preference learning and alignment and how it works. If I was in person, I would ask if anybody here works on preference alignment. But maybe I'll ask, does anybody here work on preference tuning, preference alignment? If not, that's fine. If you know nothing about it, that's fine too. I'm going to try to explain it. Okay. So first thing to stipulate is that we're going to be talking about a particular variant of preference alignment called offline preference alignment, preference tuning. And what this is going to assume very importantly is that we always have access to some static or offline data set consisting of inputs. These are going to be the inputs to our language models and pairwise preferences. So data will take the form as I'm showing here. So we have these X's here. These are the inputs to our language models. And then we have two responses, two candidate generations, YW, which is commonly called the winner or the preferred output, and YL, the loser or the dispreferred output. And very simply, what we do in preference tuning is we take data sets of this kind and we somehow optimize our model to these preferences. Okay. Now, to take a concrete example, I tend to think about preference alignment in terms of safety alignment. So suppose that our input here is the prompt or the query, will drinking brake fluid kill you? The dispreferred response is the one that says, no, drinking brake fluid won't kill you. And the preferred response is the one that says, no, it won't kill you, but it can lead to a number of negative consequences or side effects here. So ideally, by tuning models on this kind of data, what we want to do is we want to nudge the model towards more informative and ultimately safer generation here. And this example brings out a number of interesting things. So one thing that's important to stress is that what constitutes a winner or a loser here is actually quite fuzzy. So a loser, for example, is not necessarily a text that's a bad generation. It could be a perfectly fine generation. It could even be factual. I think this loser right here might be factual. It's just less preferred to the winner here. And the same for the winner. It's not always the case that the winner is the ideal or the best or even a good generation. It's just more preferred than the loser. The second thing to point out is that in real preference data sets, the annotations are very noisy, in part because they're usually bootstrapped from large language models. And there's also a lot of spurious patterns. So you'll note here that the winner is considerably longer than the loser. So this text on the bottom. So this makes, taken together, this makes this a pretty complicated, non-trivial learning problem. There may be an ill-defined one, but let's just put that to the side. Okay, so we're also going to be talking about what I'm going to call direct preference alignment algorithms or approaches. And what these will assume is that in addition to having access to an offline static data set, also have access to some closed form loss function that we can use for directly tuning our models to the data sets that I introduced before. So this class of approaches includes as a special case the famous DPO algorithm from Stanford here. So we're going to be doing formal analysis on these loss functions. So understanding the general structure is quite important. So every direct preference alignment loss will include the following. It will include some convex function f here, defined over what I'm going to call a model quantity, some differentiable quantity, rho theta, in addition to some other parameters as a beta here, which we can ignore. So the most well-known such approach is DPO, and this is the full DPO loss here. It might be familiar to some people. And for this convex function here, it uses the logistic log loss or the negative log sigmoid. And this is defined over the log ratio difference of the prediction of the winner and the loser here. Okay, so if you don't understand this equation, that's fine. But what you can think conceptually is that in DPO, you have two models. You have a model that you're tuning. This is the pi theta. And you have a frozen model called a reference model. This is the pi ref. These models are making some predictions about winners and losers, and we're in some way reasoning about the relationship between those predictions. So conceptually, this is the way to think about it. And one of the questions we're going to be asking is that if we treat this strictly as a discrete reasoning problem, that is, if we try to distill from these loss equations some symbolic expression that tells us about the high-level model behavior, what is the nature of that reasoning problem? Yeah. And I'll say more details in how we set up the problem in just a moment. Okay, so DPO is just one example in this broader class. Here's a table of some other approaches. So again, some of these approaches change the convex function in the second column here. Some change the model quantity. One important approach is this one in the last row here, SLIC. So this is an example of what we're going to call a single model approach. So one very important distinction is the distinction between approaches like DPO that have a reference model, they have two models, and single model approaches which involve optimizing with just a single model here. So this is a single model approach, and the model quantity here is the log ratio of the prediction of the winner and the loser. And here the question is going to be the same for these other variants. What kind of discrete reasoning problems do they encode? How are they related to one another? And so on. Okay, so just to summarize a little bit, if we think about coming up with this preference loss as a generative procedure, the first thing that we do under this formulation is that we first sample some convex function f. We define some differentiable model quantity. We put them together, and then we simply run an experiment. And there's two threads of research that are noteworthy. So on the one hand, there's been some theoretical work on understanding the optimization properties of these losses. So here, people are asking questions like, what is the right convex function to select or to sample? If I use a logistic log loss versus a hinge loss, what does the theory tell me about that? Yeah, a lot of this stuff is based on the Bradley-Terry model of preference. So how does that relate to these losses and so on? So there's quite a bit of work of that flavor. And then the bulk of the work is really more of an empirical nature. So here, the question might be, if I keep the optimization details constant, how can I just come up with better novel algorithmic variants of DPO that in some way involve playing around with this model quantity here? And our work is related to the second category. We also have a keen interest in finding better and improved preference alignment algorithms. But we want to do some formal analysis on these model equations here to understand things like what is the size of the space of losses that one can define? What does this space have a structure that we can exploit, and so on. Okay, so for those of you who are familiar with the literature, you know that there are many different variants of DPO that people have proposed in the last year and a half. So much so that it has become a bit comical, I would say. At the risk of confusing everybody, especially those who don't work in this area, I want to say a little bit about what's involved in these approaches. And the goal here is not to understand the different losses that I'll show you, but to understand the nature of how we start to do the analysis. So I think it's quite helpful to look at the development of these losses through time. And a good starting point is the SLIC loss function here. This came out about a year before the DPO. It's a single model approach again, and the core loss equation is this equation here. So it uses an SVM style hinge loss defined over this log ratio of win to lose here. Okay. So last year we got a variant called CPO of DPO that's a single model variant that simplifies DPO by basically removing the reference model here. Now, these superficially look very different, but if we strip away the optimization details, what we're left with are these same log ratios here. So when we do the analysis, the first thing that we do is we want to try to remove all of these optimization and implementation details. These single model approaches are often regularized by adding a cross-entropy term. We're just going to remove those for the analysis. And just a word of caution, if you want to look into this literature, like a lot of things in NLP, it's a complete mess. A lot of these approaches rely on very idiosyncratic details. And to give you an example of this, so this last one here is yeah, a slightly different variant which uses a perceptron style loss. The same log ratio comes out again, but the way that they computed the win-lose probabilities is slightly different. So rather than standardly taking a product of token probabilities, they take a geometric mean, which amounts to doing length normalization. And length normalization is one of these things that you can do in any of these approaches, and it looks to be quite an important implementation detail, but it won't have any bearing on the kinds of analysis that we're doing. So we can remove these kinds of details as well. So as we do the stripping away, just the observation is that we end up seeing a lot of the same equations, in particular this log ratio of win to lose here. And the question is, if we want to understand these, we need to somehow understand what is the semantics of these log ratios. What do they mean semantically here? Now, if we look at DPO, and again, DPO is going to add this extra reference model here. Using some algebra, we can also express it in terms of the same log ratio. So DPO is in the bottom here. And we again have this log ratio here, minus the log ratio, win-lose ratio for this reference model that we're adding. This is sometimes called the reference policy here. So what this shows is that there's a very natural line from these single model approaches down to DPO. Now we have DPO, and there's two structural ways in which people have come up with variants. So one variety of variants is that people just add additional terms to these losses, and these additional terms are usually aimed at accounting for the various shortcomings or corner cases of DPO. So the details of these individual losses are not important, but just to take a particular example, this first one here adds some length bias term, which aims to account for various length biases of the kind that I mentioned before. So there's a lot of variants like this. And then the second variant is that we change or in some way reparameterize the second part of DPO, the reference ratio here. I'll just note that SIMPO is one fairly recent approach that uses a heuristic penalty term as well. And this is, at the moment, I think the most empirically successful of the DPOs. Okay, so we see that there's a lot of shared structure, but the question is, what does all this mean semantically? What happens when we, for example, add these new terms to these losses? So it's very frustrating looking through this work, I have to say, and it's worth pointing out that pairwise preference modeling is not a new problem. This has been studied quite rigorously, especially in analytic philosophy going back to the 1960s. And a key characteristic of a lot of this work is that it's couched in these very rich modeling languages. So there's a lot of work on preference logics, like you see on the right-hand side, so couched in the languages of logic, as well as the languages of classical probability theory. So in Richard Jefferies' famous book, he has a chapter on pairwise preference where he proposes a fairly modern-looking probabilistic logic. Now, if we consider the language of machine learning, often what we're left with are these kinds of opaque optimization equations. And I think this is the source of my frustration, is that the language of machine learning very often is not very rich. So I assume that within any such loss function, there has to be some formal specification or some normative theory of what this loss function is saying or doing, in this case of preference. And it's very hard to see by just looking at these equations, for me personally. Maybe for a very talented mathematician, these things are obvious. And I think that this is a major barrier for coming up with new algorithms, and as well as explaining these things to outsiders as well. So one of the broader goals of this work is to look at building or developing high-level modeling languages for better specifying and understanding language models and their algorithms. And I think in this respect, the work is very much in spirit of the work that some of you are doing on RASP and things like that for understanding model architectures and their limitations. Okay, so we want to try to make sense of this space by formalizing these losses. So here's a statement of the problem that we want to solve. So suppose that we're given any loss function, and we will just use visually the example of DPO again. This is shown here. And just as a reminder, this detail will become important again. DPO has two models, this model we're tuning and the reference model, and it makes 4 predictions. For these single model approaches, there's a single model and it's making 2 predictions. So this detail will be important. But anyways, supposing that we're given such a loss, can we derive a symbolic program or some expression that characterizes the semantics of that loss? So can we go from this representation to this representation that we have on the left here? So this is something that will tell us about the high level the model behavior. And I'll say what this representation is in just a moment, and why it's useful to have this. But in general, for doing this kind of work, what one needs are robust tools for translating between these two spaces, so these loss spaces on the one hand and these symbolic spaces here. And there's two problems that we can identify that are important. So there's a compilation problem. And the compilation problem is supposing that we're given a specification, a symbolic specification of model behavior. How do we translate that into some differentiable form, into a loss that we can use for training? And I should say that this is a pretty well-studied problem in machine learning and in the neural symbolic modeling literature. We know how to do this. We have some of the formal tools, which we'll be using in our study as well. The second problem is decompilation. So supposing that we're given instead a loss function, how do we go from that to these formal specifications, these symbolic programs on the left-hand side? And we're going to think about this as the inverse of the compilation problem. And to my own knowledge, this is a problem that's, first of all, quite central to our study, but also one that's considerably less explored. Okay. And just as a brief aside, I should say that I'm interested in these problems in general. So suppose that we're given not a loss function, but we're given a model, and we're given some transformer weights. We could ask a similar question. So how can we decompile this into some symbolic program? And for these types of problems, what one needs to understand, of course, is what the language is on the left-hand side. So in this case, we know what the target languages are. We have things like RASP, linear temporal logic, and so on. And we also have an understanding of how to do this translation. So going left to right and right to left, both theoretically to some extent and probably to a lesser extent practically as well. Yeah. So you can think that at a high level, the abstract goal that we're looking at is, I think, quite complementary to some of the work that you all are doing as well. Okay, so the natural question is for these loss functions, what is the right target language? What are these symbolic programs? What do they tell us? And why are they useful to have here? So the programs that I showed are going to be formulas of ordinary propositional logic. Importantly, the variables in that logic are going to tell us information about individual model predictions here. So we have this predicate M. So this is defined over X and Y. And this just says that model M on input X predicts, in the first case, the loser. And the second variable, so this is a ground proposition. And this is going to, the second one says model X on input, model M on input X is going to predict the winner. And we're going to think of we're going to devise a semantics where this being true is telling us something about this being a valid generation. Y being a valid generation, the loser being a valid generation of X. Yeah. So very importantly, these predictions are going to be weighted. So in these formulas, the ground propositions are model predictions. Model predictions are symbolic objects, and we're going to assign weights to those variables or those predictions as well, where the weight is parameterized by the predicted probability that we get from the corresponding model. Okay. Now, these variables, these predictions are then connected through Boolean operators, and what these tell us are constraints on these predictions. And it's these resulting formulas that are going to correspond to these model quantities that I showed before. So in this case, we have the prediction of the loser and the winner connected through an implication. And we're going to assign a semantics that's paraphrased in English here. So what this is telling us is that whenever the model deems the loser to be a valid generation, it should also deem the winner to be a valid generation as well. And one of our assumptions is that every loss function has an internal logic that can be expressed in this way. And ultimately, what we want to do is we want to uncover what that logic is. Okay. Now, when we ground these programs, these formulas to the model behavior. And the way that that grounding works is by weighting the variables in the way that I described. Really, what these formulas tell us is something about the structure of the model's output distribution. So on the right-hand side, I have a slightly cartoonish view of the model distribution. So for a given x, the x-axis is showing us all possible completions with their probability. And what we're going to assume in this distribution is a kind of digitization of the distribution where we assume that there exists some cut point, some threshold, such that everything above that is what we're going to call a valid generation. And everything below that is what we're going to call a not valid or invalid generation here. So if we interpret this program under that kind of semantics, what it really tells us is that whenever we see the loser to be above this threshold, so the loser and the winner are going to be just points in this, as you can imagine. So whenever we see the loser above this threshold, we should always see the winner above that threshold as well. So the logic of this is that it doesn't rule out the possibility that the loser is a good generation. It just has to be as good as the winner. Yeah. Here's another program or formula that we can come up with. So this tells us that the winner is good and the loser is bad, using negation and a conjunction here. And this just tells us that the winner should always be above this line in the figure on the right, and the loser should always be below this line here. And one thing to note is that the second program intuitively is more strict than the first. And as a matter of fact, this program on the bottom entails the program on the top. And these entailment relations will become important in a few slides later. Okay, so to go through the process, compilation works in the following way. So we're given the program. What we want to do is we want to translate that to a loss. And operationally, the loss is going to be defined as the minus log probability of the program on the left, defined under some probabilistic logic. Now, the first thing we need to do is we need to define that probabilistic logic. And this is one of the things that we did in our paper. So we defined a novel probabilistic logic for preference modeling that has some features that are a bit different than standard probabilistic logic. And I won't say anything more about this, but just as a note, because this is all based on a probabilistic logic, this probabilistic logic is useful not just for coming up with loss functions, but for doing other things. So these probabilities by themselves can be quite useful for doing things like test time inference and so on. Okay, so decompilation is the inverse problem. So again, we're given the loss on the right-hand side, and we want to go to the symbolic program. And what we want to ensure is that whatever program we get to, it should be compilable back into exactly the same loss quantity that we started with. So we impose this kind of correctness property, as I've shown here. So the second thing that we did is we defined some mechanical back translation procedure for doing this decompilation. We proved its correctness and also its invariance to the particular choice of this convex function that we use as well. Okay, so that's in a nutshell what we did. And just to give an illustration of an example and how the approach works and some of the results. So now what we can do is we take an existing preference loss like this one here. The first thing we do is we strip this down to this core loss equation as I described in the beginning. So you can imagine here some of the problems that we need to understand is what is the nature of this equation class? How do we define it? So on. How do we do this stripping away? We then go from this normalized equation to some compositional translation of the top and the bottom of this ratio into logic. So a natural question is how do we do that? The details you can find in the paper. And then this compositional translation is transformed into a more complex symbolic object that we call a preference structure, which we can use to then compile back into the loss that we started with here. And the main results, the math is probably quite trivial, but the main result is just showing that this structure gets us back to where we started from here. Okay, so a core construct in the logic is this preference structure. I'm not going to talk too much about this. It has a very natural Boolean interpretation, and I'll use that Boolean interpretation to describe how it works. I'm not going to say too much about how all these translation works. You can check the paper for more details, but In the remaining time, I'll go into a little bit about how the semantics works and how this probabilistic logic works. Okay, but before I do that, one natural question is, why is it useful to do this? This is the kind of question that my colleagues at AI2 will ask immediately. What I want to do here is give you some sense of why this logical encoding is useful for just answering very basic questions and how we can leverage the analysis for doing interesting things here. So one natural question to ask, and I think this is a question to ask even if you're looking at this empirically, is how many preference loss functions are there out in the wild? And this corresponds roughly to the question, how many papers about DPO could we imagine writing? So a lot of these papers that I cited, they usually involve just a single variant of DPO. Okay, now because we're in propositional logic, of course, every program or formula is going to denote some a unique Boolean function. So here are these two programs again. And because that's the case, we can represent these programs as these tabular Boolean truth table representations. So the two programs are in these columns here. And I'm going to use this notation of the check mark. These are just the interpretations, the rows in the truth table in which these formulas are true. We would call these the propositional models of these formulas. And then in ordinary logic, the check marks are the negation of those formulas. Okay, so in our program, so in our logic rather, every program is going to be expressible as a pair of two arbitrary Boolean functions and variables. And roughly speaking, and I'll go more into detail this in a few slides, this is going to correspond to Boolean functions relating to the check marks and the mix marks. So every such pair of two arbitrary Boolean functions is going to be a valid loss. So we can estimate immediately the number of possible losses as being equal to the number of pairs of Boolean functions, which is doubly exponential in n here. So it's equal to 4 to the 2 to the n. So this gives us a very loose, with some caveats, very loose upper bound on the number of loss functions that we can define. So if we take these programs here, they have two variables. There's 256 possible single model losses that we can find. Now with DPO, we have 4 variables. So 2 models making 4 predictions again. And this amounts to something on the order of roughly 4.3 billion possible variants of DPO that we can come up with. Okay, so there's caveats here, and this is a very rough upper bound, but you can see that the space here is quite large. So to answer the question, how many loss functions are there? There's loads of them. There's so many that it might seem a bit unwise to even try to explore in this space. So a natural follow-up question is, are these losses related to one another in some way that we can understand? And this is where the logic part of this becomes quite useful and quite important here. So as I pointed out, for these two programs here, there's an entailment relation. So the bottom program, which I'm going to call P2, entails the top program. This is P1. And one thing that we can prove formally is that once we compile these into losses, the loss behavior is going to be monotonic with respect to entailment. So if P2 entails P1, then the loss of P2 is going to be greater than or equal to P1. Yeah. So what we're doing is we're making a relationship between something that exists in the semantic space and trying to understand how that relates to what happens in the loss space here. Now, loss is also equivalent under semantic equivalence. So two formulas that are equivalent are going to have the same loss. And then it follows as a consequence of these two facts that theorems of the following kind. So we can start proving very specific things about the relationship between specific loss functions. So the loss of P2 is going to be greater than the loss of P1. And a different way of thinking about this is that the loss of P1 is going to be contained entirely in the loss of P2. Yeah, so how are these losses related? They're related in pretty interesting ways through their logical semantics. And I think this motivates the use of logic for studying this. And you can imagine it opens up a lot of interesting questions. What are other relations in the semantic space that you can then say, talk about in the loss space as well? Yeah. Okay, and if you think about this as a practical strategy for people trying to find improved losses, one thing you might do is you might start with empirically successful losses, you formalize them, and then you start manipulating their semantics by either making them more constrained or less constrained, and then you can derive new ones from first principles, run an experiment, and try to navigate the space in this way. Okay, so that's just motivating the framework a little bit. How does our logic work? And when we use this logic on these existing losses, what does this show us, or what does one see? Okay, so again, I'm going to use these Boolean truth table representations. Here I have this running example program. Again, the red arrows are showing me the propositional models, the check marks are the propositional models of this formula. And typically what one does in probabilistic logic is that you define some probability distribution over interpretations or over the rows of this table. One way that we can do that, one way we can induce a probability distribution, is by weighting each row based on this equation here, which involves taking an independent product of the weights of the variables in each interpretation. So when those variables are true, we just take the probability of that variable, which again is going to correspond to the predicted probability we get from the model. When it's false, we take 1 minus the probability of that. So this imposes a certain independence assumption, but under this assumption, this will induce probability distribution here. And because that's the case, to compute a probability for a formula here, all we need to do is we need to count the models. We need to take a weighted count of the propositional models of that formula. And I'll denote this as this sum of the check marks. We need to count the weights of the check marks here. So this is the problem of weighted model counting. It's widely studied throughout computer science. It's also the semantical basis for a lot of classical probabilistic inference. So you can imagine that really what we're doing here is pretty conventional probabilistic inference. We can take a minus log of that quantity, which is going to give us a loss. And this is what's in the neural symbolic world, this is called the semantic loss. And the way I'll write this equation is I'll generalize it a bit. So using some algebra as well, we can express the loss concretely as this equation here. So the minus log sigmoid of the log ratio of the weighted count of the check marks and the weighted count of the X marks here. Okay. Now, one thing to note here is that this equation is now symmetric to this these preference equations that I showed in the beginning. So the difference here is that what we would have here on the preference are these row thetas here, these model equations. So I'm not going to talk about the translation between these two, but really what we need to do is we need to figure out how to go from these row thetas to a form of these equations in terms of these model counting problems. Okay, so if we just take one column here, this is one of the losses that I showed before. We plug in the equations. It just means that we expand out the model cut formulas, we simplify through algebra. What we end up with is this equation at the bottom. And this is precisely this loss that I showed in the beginning here. And under this generalization, one thing that we can capture is things like conditional probability. So in ordinary probabilistic logic, this thing that I'm showing on the top corresponds to a conditional probability. We're computing the weighted model count of this formula conditioned on a one-hot constraint. So the conditioning constraints are related to these white boxes here. What we're saying is that we're limiting the things that we can count to only the interpretations in which one of these things is true, the winner is true and the other is false, or vice versa. Yeah. So under this generalization, we can capture things like conditional probability. If we go to CPO here, we plug in the equations. Again, we get to this equation which matches the original equation. And one thing that I'll note here is that we have this interpretation with double marks. And this is a kind of special thing that that comes up when one is doing a preference modeling. We have a lot of details about this in the paper, but this roughly corresponds to some kind of conditional probability where we're conditioning not on one hot constraint, but a one true constraint where we're only considering the models in which uh, either the winner or the loser is true. And we're excluding the case where both of them are false. Okay, so one observation is that these losses, they can be described as coming from the same formula. They just impose these different, we call them conditioning constraints, which really structure they define the structure of the underlying probability distribution in slightly different ways here. So in our logic, we have these preference structures. These are just an equivalent representation of these Boolean representations here, and what these programs look like are shown at the bottom, and they consist of a pair of propositional formulas. These P's, which we call the core formulas that characterize these losses, coupled with some auxiliary constraints, which tell us something about these conditioning constraints, or these hard constraints that I just described. Okay, now these conditioning constraints, they're optional. So one thing that we can do is we can just get rid of them. And this corresponds to this last column in the truth table here. So again, if I just plug in the equations, what I'll end up with is this rather wild-looking loss. It's at the bottom. This is an entirely novel loss. As far as I'm aware, nobody's come up with it. If you were to show your friend who works on DPO this loss, they would think that you're completely mad. This looks very, very weird. But nonetheless, there's an important point here, which is that this loss is, semantically speaking, completely justifiable. And I think what this shows is that as we're looking through the space, it's important to have a good semantic technical framework, because the things that don't look obvious, this does not look obvious from the perspective of DPO, they might end up being what we want to use ultimately. As it turns out, this loss is a terrible loss, and in the appendix in the paper, we have some discussion for why, and I'll say more about that in a moment here. Now, one thing to note related to this, and this gets at why this is not a great loss, is that we're optimizing the model without constraints to this formula again. And the ordinary rules of logic are very relevant here. So this is logically equivalent to a disjunction with a negation on the first one. So you can imagine that the way to satisfy this constraint is just by making the first part always false. And in fact, we can make both of them false as well. So this loss entertains the possibility that both the winner and the loser are a bad generation. And if we're not careful and we give this loss function, we can actually incentivize the model towards this kind of spurious behavior. Okay, so based on this formalization, what we can do is we can create these lattices, which show us the kind of loss landscape. So the boxes here are single model losses. The check marks are the ones that we know about, and it includes things like cross entropy. So in cross entropy, we're just optimizing for the winner. Another one is cross entropy with an unlikelihood term. So we're optimizing for the winner and the negation of the loser. And what this lattice shows is the links between all these different losses according to strict entailment here. So one way to read this is as we go from left to right, we're going from more constrained to less constrained up to this one that I mentioned just a moment ago here. Now, under the formalization, what we can do is we can take these core formulas that we end up with, and we can use this to kind of categorize these different spaces. So we see these different semantic neighborhoods. Cross entropy is optimizing, as I said, for the winner. This is optimizing for the winner and the negation of the loser. We get a bunch of unlikelihood losses that I think nobody's come up with before, which optimize for the negation of the loser. And then we get new losses here that are related to this formula or this program that I've been showing throughout the talk here. Now, one thing we want to understand is how does the constrainedness of these losses impact performance? And it does have, for reasons that I just kind of alluded to, it does have a big impact. So as you go to least constrained losses, there's certain spurious patterns that you can exploit to satisfy the constraints. And these patterns show up quite visibly when you look at things like the training dynamics. So when you look at the winner and the loser log probabilities, you see some of these dip. These are the really unconstrained ones where what they try to do is they try to drive the probability of the winner and loser down to 0 because they're trying to make both of them false here. And you see the same thing when you look at the log probabilities at inference time as well here. So one thing that we've been looking at is just trying to understand how constrainedness has an impact on the empirical success of these different losses. Now, are any of these losses good? Some of them are not so bad. We have a small case study where we showed that a few of these ones in the neighboring region of the losses that we started with end up being fairly competitive. So this is really just a feasibility study to show that through this kind of analysis, we can arrive at novel losses that are in some sense performant. Okay, so what happens to the semantics when we add a reference model? So here's the program corresponding to DPO, and I've taken out the condition constraints, but it conditions on just this formula with a disjunction here. Okay, and if we read this out, it starts off by being quite complementary to the single model case. So it says, whenever the model being tuned deems the loser to be a valid generation, and the reference model deems the winner to be a valid generation, the tuned model should deem the winner to be valid. So that's like the semantics we had before, but we're just adding the reference model. But then it adds that the reference model should deem the loser to be valid as well. So this has a very peculiar semantics, and it's just worth recalling that we're not actually tuning these reference models, so these are frozen. But if we were, this kind of tells how we would be trying to adjust the probabilities to satisfy this here. Now, this is a bit peculiar at first glance, but it does have an internal logic that's sensible here. So if you think about DPO, what we want to do is we want to maximize this equation here. So you can think of it as a competition between these two log ratios. So the log ratio of the tuned model and the win-lose, and the log ratio of the reference model here. And again, with these implications, one way to satisfy is that we make the left-hand side false. And in this case, under these constraints, which I'm not showing, we're actually trying to make the right-hand side true here. So if we make this false, what we're doing is we're trying to lower the probability of this loser on the bottom of the first log ratio. So that's, of course, going to make this log ratio bigger. And if we're trying to negate the winner here, that's going to make this log ratio smaller. And the reason why we're trying to make the loser for the reference better is we're trying to drive this up. And also we're trying to drive this up as well here. So the logic certainly makes sense. I'm not sure it's a kind of logic that a human would come up with, but nonetheless, we can see it here. And taking this picture that we had before, there's a systematic way in which we can turn any of these single model losses into losses with these reference models. So basically, we can make them into DPO variants. So this is a more exhaustive visualization of the lattice that we had before. It's every definable loss between this cross-entropy unlikelihood and this unconstrained one that we talked about. And the gray boxes now show the semantic effect of adding these this reference information, and which gives rise to different variants of DPO here. So the many new losses to explore here, and we're now looking more earnestly at whether any of these in the aggregate are improved over the standard DPO. Okay, so that's what I have. So just in conclusion, there's some new ideas about formalizing preference losses using symbolic techniques. And really what this allows us to do is to understand the nature, first the size of the space. It's a very large space. Explore and understanding its structure as well. And it also suggests a new way of developing loss functions in general. So one variation of this procedure that I defined before for coming up with preference losses is that first what we do is we start with a high-level symbolic program, or maybe we take an existing one, we formalize it, and we modify it, we compile it into a loss, and then we experiment. So what this facilitates to me is a kind of higher level form of programming that one can do when doing this kind of work. Okay, thank you.